Okay, so yeah, okay, thank you, Miguel. So thank you everybody for being here. It is a big pleasure to be here and have the opportunity to share some of the research that myself and my group we are doing on free energy minimization in environments that are ambiguous or adversarial. So I will start with some motivation. The core of the talk today will be on computing optimal actions. So we are going to try to motivate the problem of why we should care about ambiguous or adversarial environments and why it is important. Then I will introduce our main results, which is basically a computational model that enables free energy minimization across ambiguous environments. And finally, as an engineer, I would like to discuss some of what we see as cognitive implications of our model. So let me start from the beginning. Well, computing optimal actions. It is undeniable today that we have a lot of computational models, machine learning, artificial intelligence models that are optimal, that are able to outperform humans in many domains. For example, today it's not difficult to build a model that allows the robot in the picture to outperform the child that is doing exactly the same task. What is the issue, however? The issue is that these computational machine learning models are actually quite fragile to perturbations. So if you see the setup in the figure, the robot is in a closed environment. And it is known that machine learning models can be really non-robust to even small perturbations that can cause catastrophes, literally catastrophes, such as car accidents, just to make a famous example. Now, as a control theorist, I believe that this robustness can be handled by designing better computational models. Better means computational models that are optimal, that allow computation of optimal actions, but that are also robust to perturbations in open, unstructured environments. And of course, control is only one ingredient of that. To tackle this big challenge, we must design models that are really the intersection of different disciplines. And here is the connection with free energy. So the key ingredients that I will use today are going to be a version of variational free energy minimization, of course, optimal control, and tools from infinite dimensional optimization. The results of this interdisciplinary approach will be a new computational model that consists of two key ingredients. So the first one is a problem formulation. And the second is a set of resolution methods that actually allow to solve the formulation, so actually allow to minimize free energy amid ambiguity. And then I'm sure I don't have to convince anybody why this would be important. On one side, of course, this model could give a normative framework explaining behaviors for natural behaviors for natural agents. But we could also use the model to engineer better artificial agents that are able to robustly minimize free energy. And of course, many of the things I'm going to say today are based on novel mathematical methods. So there is kind of a niche of mathematical problems that has been kind of unexplored up to now. And so I'm going to use the model in the context of autonomous decision-making. So let me try to introduce what are the key ingredients of this problem. Well, of course, there is an agent, and the agent interacts with an environment. Now, the agent has a model of the external world. So the agent has a model of the environment. Formally, we are capturing this model of the environment with a conditional probability density. So this is P bar, is the probability that the environment will evolve in a given way, given the current state and of the world and the current action, which is UK. So, unfortunately, the environment is not, however, the same as the model. So the environment, of course, can be nonlinear, stochastic, and even non-stationary within our framework. And moreover, in addition to this, it is also subject to perturbations. So perturbations are basically phenomena that are not known to the agent. So as a result, as a matter of fact, the real world is different, so is not the same as the environmental model. And we describe this again with a standard terminology, which is a conditional probability function. So what happens between the agent and the environment? Of course, the agent must sense something. So by x k minus 1, we denote the current observations and beliefs of the agent for anything that is relevant for his task. In control, and I'm going to use this word, we say that this is a state variable. Then what happens? Based on this information, the agent wants to minimize free energy to determine an optimal action. Very good. So this means that the agent has access to a generative model and to some subjective preferences. Now, subjective preferences are basically costs, associated cost functions in terms of actions and states. And the generative model gives to the agent an ideal behavior. So the generative model captures what is the behavior that the agent would like the environment to follow. So it is a sort of a template for the external world. So it is the agent wish list, we might say. And you see that it has two probability density functions, one for the state, xk, and one that is going to be for uk, which is the action. So in essence, this is an ideal behavior or a reference behavior that the agent would like the state and actions to follow over time. Based on this information, I will clarify this more in detail in the next slides. The agent outputs an action. So UK is the action at time step k, and it is based, of course, on the generative model, on the preferences, and on the current state. Just as a disclaimer in terms of terminology, you will see upper and lowercase letters. Uppercase means that we are considering a random variable. Lowercase, it is a realization. The subscripts, like the K here in the environment, are always going to denote the time dependence. And in bold, we have vectors. So by the subscript K here, we mean that the environment can change over time. So we say that the environment is non-stationary for both the environment and actually the environmental model, and as well as the generative model. So let me try now to formalize, given this setup, what are the interactions between the agent and the environment, and where free energy comes into place in this context. So let's say the environment starts from a given prior. This is just a probability density function of x0 at the initial time. Based on this information and based on the generative model and the subjective preferences, the agent computes an action. In the context of this talk, the action is going to be sampled from a randomized policy. So the policy P UK given xk minus 1 is again a conditional density function. Basically, given the current state, it gives a probability for the next action. And the next action is in fact sampled from this probability, and it is sent to the environment, to the external world. Now, the world, again, behaves differently from the environmental model. So as a matter of fact, the next state of the agent is not sampled from the model, but is going to be sampled from the real world. And this generates a state that the agent takes into account, and this process goes on and on. So over time, you see an exchange of state and actions. Let's say this goes on from time 0 up to time n. And formally, this is captured by a product. So we have a product of all these conditional probabilities from time step 1 up to the end of time n. This is basically a big joint probability density that I'm going to refer to as a closed loop behavior with a shortened notation P0n. So the closed loop behavior expresses what is going to be the exchange of information between states and actions. And I could do exactly the same for the generative model. Remember, the generative model provides a template for actions and states. So I could do exactly the same here and build a big joint probability functions that captures the desired behavior of states and actions from the generative model. And I'm going to refer with this with the symbol Q0n. Now, the subject of our design is actually the policy. So with this, the model that I'm going to present, we are going to find what is the best policy, and this is obtained via free energy minimization. So what is the policy that minimizes a variational notion of free energy? So let me try to go a little bit more in detail into this. So as a disclaimer, we are going to use the variational free energy. So we are going to obtain a policy by minimizing a notion of complexity plus an expected loss. Now, following standard information theory concepts, the complexity is captured by a term, which is a Kullback-Leibler divergence between the closed loop behavior P and the behavior of the generative model. So this somehow captures the complexity of the closed loop system, the closed loop behavior, versus the behavior of the model. The Kullback-Leibler divergence is a tool that measures the discrepancy between two probability densities. It is not, unfortunately, a distance, but for our purposes, this is as good as it goes. The expected loss, well, is just an expectation of state and actions over the closed loop behavior of the system. So this symbol here means that we are taking an average over the closed loop behavior, so over the state and actions that are exchanged between the agent and the environment. And the problem of minimizing free energy, of finding the best policy that minimizes free energy, can be mathematically translated as a minimization problem of the cost function I just introduced. Just one remark, actually a couple of remarks on this problem. This is an infinite dimensional optimization problem because the decision variables are not vectors, but are rather functions. The curly brackets here denote a sequence of policies. So we are not looking for a single policy, but we are looking for a policy at every time step. In other terms, we allow for the policy to change from time to time. And of course, the result is going to be an optimal policy that is a compromise between complexity, which is the DKL, and the expected cost, which is the expectation of the state and action cost functions. So first of all, before jumping into motivating ambiguity, let's see if this is actually a problem. Let me consider two environments for which the environment is different from the agent model. Okay, as the first environment I'm going to consider is a simple linear system, which is a ball and beam system. So the goal here is that of stabilizing this ball here, the blue one that has a given mass, and to do so, the agent can basically regulate the angles. So UK, the actions are angles, and XK is the position. The other environment I will consider later is the routing of a robot in an unstructured environment. Okay, so for now, let's stay with the ball and beam, the regulation problem. We want to keep the ball at the 0 position. Well, it is known from physics that for small angles, this system is captured, the dynamics of this environment is captured by a simple linear relationship that links the current state, the current position, xk minus 1, and the current control action, UK, to the next position of the ball. So the control in physics, this is simply say the linear system. And to this, we are adding some noise, which is uncertainty about the position of the agent. Let's say the noise is from a normal distribution, okay? Well, this dynamics is completely equivalent in writing a conditional probability function. This is our world model, P, xk given xk minus 1 UK, which is just a Gaussian distribution, a normal distribution centered into the dynamics provided by the environment with some sigma, which is the variance of the noise. We could do exactly the same for the model. Now, this is the model that the agent has. So, and this is different, as you see from the environment model, in one parameter. Okay, there is a different 116 in 1.0.2, which is basically less than 10% in discrepancy. So it is very small. The result is a p-bar that is a Gaussian distribution with a given average that's slightly different from the real world and the same variance. We have even assumed the same variance. So as a matter of fact, the model differs from the real world. And this discrepancy can arise really very simply in practical terms, because it is this parameter that I highlight in red is just due to the friction or mass of the ball. So we are basically saying that the agent knows that the system is linear, but does not know exactly the friction and the mass. Let's couple this setup with a generative model and with the preferences. So the generative model, again, expresses the wishes of the agent. So the agent would like to keep the ball, let's say, in the 0 position with some variance, with some probability. So this is expressed with a Gaussian distribution, a normal distribution centered in 0 with a given variance. And the same for the policy. So when the equilibrium is achieved, of course, the agent would like to apply no control input with some probability. So this is the generative model. The quadratic cost can be the simplest cost we can imagine. So the cost can be the simplest one we can imagine, which is quadratic. So this cost measures how far the ball is from the rest position. The only minimum of this function is clearly the position 0, where the agent wants to keep the ball. And now what happens if we solve the free energy minimization problem I just introduced, assuming that the agent does not know that the real world is different from the environment? So in other words, the agent does not know that its model is different from the real world. Well, the result is really the opposite of what would be the agent goal. So in other words, rather than stabilizing the ball at 0 position, you see that this over time becomes unstable. So the position of the ball becomes bigger and bigger, meaning that the agent fails this very simple task. Well, and this is just a setup. Again, linear system, one-dimensional, simplest generative model and cost functions, and still we have this kind of phenomenon. Clearly, things can scale up really badly if we consider more complex scenarios, such as the robot that we were considering at the beginning, and with failures that can be catastrophic for the robot, but also for others, assuming that the robot was maybe sharing the environment with somebody else. And this is exactly what we want to address with our model. So with our model, we will see that we can mitigate the undesirable behavior that we just saw, and we will minimize free energy across ambiguity. The model will also give us what are the policy limits and will give some interpretability properties of the policy, and will show clearly what is the role of ambiguity in decisions. So actually, in a very counterintuitive way, to minimize free energy across ambiguity, we will see that there is a free energy maximization step involved. And that's, to me, the first time that I found this phenomenon. And I would be happy to see if we are missing something here. By policy limits and interpretability means that we can give rigorous algorithms that allow to compute the optimal policy and estimate its impact. And finally, the model is able to explain behaviors. So let me jump now to what is actually our model, so our main results. So the first thing to do is to formalize what is environmental ambiguity, which I mentioned up to now, but I really left it as a kind of intuitive concept. So I would like to clarify it once and for all. Remember that the environment and the model are different from each other, and they are both probability densities. This means that if we look at the space of densities, just if we wanted to represent it as a two-dimensional space, we would have that P bar is the environment model, and it is just a point in this space. Well, we say that the environment is ambiguous if it basically can be any probability density function that belongs to a subset of the space of densities, a compact subset of the space of densities. So basically, in other words, ambiguous environment means that the environment can be any conditional probability that is inside that ball in red that I showed in the slide. And it is convenient to characterize ambiguity with an ambiguity radius, which I'm going to call eta. From the notation, you see that eta can be time varying, so it can be non-stationary, and depends on the specific action state pairs that we are considering. Okay. How do we capture this concept in more formal terms? Well, we introduce a set, which I'm going to call B eta, centered in the model P bar. And this set is basically given by all environmental probabilities Pk, such that the decadal divergence between P and the model is smaller than the ambiguity radius for a given action state pair. So eta is the ambiguity radius, as I was just saying, and it is not constrained to be stationary or constant for all action and states, and this can be quite convenient in practice, as we will see. And it also has an intuitive explanation. So a small radius means that the agent is highly confident in the model that it has about the environment. A large radius means instead that the agent is becoming less and less confident in its own model. So there is a lot of ambiguity. And now, how do we set up the problem of minimizing the free energy functional with this new concept? Well, we want to find the optimal policy that minimizes the variation of free energy across ambiguity. So what does this mean in more detail? Well, first of all, we want to find an optimal policy. So this means we want to find a sequence of policies. By star, everything you see with star means that it is optimal here. And this policy must come from a minimization of a free energy function. So it has to be the solution of a minimization problem that involves complexity plus expected cost. However, we don't want to just minimize this cost functional. We want to minimize this cost functional across ambiguity. That is, we want to minimize the cost functional in the worst case for all environment models that belong to the ambiguity set. So the minimization problem we had before now just becomes a min-max optimization problem. If we wanted to translate this more, again, with a step towards being more formal, we would have a problem like this. So it is a very long, unfortunately, problem formulation, but it has all the key ingredients that I just showed you. So there is the optimal policy, which is the sequence of optimal policies. The free energy is again captured with the Kullback ladder plus the expected cost. And finally, we minimize across ambiguity, which means that we are actually looking to minimize the worst case free energy across all possible environments that belong to the ambiguity set. So this is going to be our formulation. This is going to be what we are trying to solve. First of all, before jumping to the resolution methods, we have been really wondering if this was a real formulation or just a mathematical nightmare, because this is basically the first time we saw this class of problems. It is an infinite dimensional min-max optimization problem. Not only that, it is also infinite dimensional, and it has nonlinear constraints and nonlinear cost functions. So to us, it is undocumented in the literature. So we started to ask if it was really solving this problem. And what we asked ourselves was if the formulation would give us something interesting when there is no ambiguity. So if we forget for a second about the ambiguity constraint. Well, what we discovered is that we obtain basically entropic regularized optimal control or optimal transport in this setting. And if we put additional hypotheses on the policy, we obtain a very popular reinforcement learning algorithm, which is Kullback ladder control. If we parameterize the policy, we obtain maximum entropy reinforcement learning. And if everything is Gaussian, we obtain a very popular control algorithm, which is called linear quadratic Gaussian regulator. But this last point is quite interesting to me because, oh, by the way, all these links have been established in previous papers. This LQG analogy is very interesting to me because it means that I could go back to the slide, to the example I showed you before about the linear system, and say that the free energy minimization is actually equivalent to linear quadratic regulator, which is a standard benchmark for my discipline, which is control. So it seems that the formulation can give something that is worth solving. So it is actually something interesting already in a very simple linear case. And then the next question is if we can actually solve the problem. And the answer, of course, is yes. And this leads me to the next part of the presentation, which is really about introducing you what is our architecture. Now, I'm trying to stay at the, let's say, the level with the least mathematics as possible. So I'm just going to give you the main flavor of our resolution methods. Leaving the theory, if you are interested, I can give you the preprint of the paper that we have. So the agent receives the state from the environment, and it has a generative model, and it has its own preferences in the form of state action costs. So our model says that the big problem formulation I showed you before can be solved in a recursive way. So there is basically a resolution engine that breaks down the problem at a temporal scale. So we have one optimization problem at every time step, and each problem can be solved by a bi-level optimization approach. In particular, first solving a maximization problem and then minimizing. What the engine gives us is rather counterintuitively to me an explicit expression for the optimal policy. So we know what is the shape of the optimal policy and the optimal value. So what is the least minimum free energy that can be achieved. In turn, the optimal value is used to build a recursion that I will go more into details soon, and the optimal policy instead used to obtain the optimal action. So what does this figure say? Well, the kind of result from the resolution engine is a probability density function, just like the one that you see here. So it is a probability of a given UK. And the action that the agent will apply to the environment is just obtained by sampling from this optimal probability. So what this shape here says, well, we have quite large probability of sampling one action, let's say between minus 0.5 and 0.5 UK. And outside that range, we have much lower probabilities. As I said, the model relies on the fact that the policy can be computed in a recursive way. And in particular, at every time step, we can show that the problem that needs to be solved is a standard minimization problem. So this is a minimization problem in the space of densities. Now, the key point here is that we are not looking for a sequence anymore, but this is just the policy at time step k. So if I want to find a policy at time step k, I have to solve this problem, which is again a free energy minimization problem. You will see that this is a complexity between the policy and the policy from the generative model Q plus an expected loss. What is more interesting perhaps is that the cost now has an additional term. This is we called this cost of ambiguity. This cost is there just because there are the ambiguity constraints. So this cost is here just because the agent model is affected by ambiguity. And it turns out that the cost of ambiguity is given by solving an additional optimization problem, a maximization problem in particular. Again, I would like just to make a few remarks here. This maximization problem in the space of the environments is a free energy maximization problem. So this is the maximization step I was referring before. This is again a complexity plus an expected loss. So what we are doing here is that we are maximizing a free energy across all possible environments that belong to the ambiguity set. So it seems actually the model shows that in order to protect from ambiguity, one must include in the formulation a cost of ambiguity, and this cost of ambiguity comes from free energy maximization. Also, from the viewpoint of the agent, I'd like to remark that the agent does not need to know what is the best, the optimal environment that maximizes this problem, but only needs to know the optimal value. And the other remark I'd like to make is that the C bar you see here is actually a cost to go. In the reinforcement learning and control literature, for example, this means that this is the best cost that the agent can achieve in the future by using the optimal policy. So it is exactly here that is the recursion I was mentioning in the previous slide. So the cost to go is actually built in a recursive way. So I can go back to our resolution methods, our model, and refine a little bit the architecture. So the resolution engine is actually a maximization free energy step. It actually has a maximization free energy step and a subsequent minimization of that cost function, which is again a free energy. The optimal value of this second minimization problem is going to be used as a recursion to build the cost to go. And the cost of ambiguity is obtained as the optimal value of the free energy maximization problem. So again, our goal is that of obtaining a probability density function that is obtained by minimizing the middle optimization problem. So the key takeaway here, one of the key takeaways is that robustness implies free energy maximization. Now, what we have to work on and detail a little bit more is this part in green in the architecture, which is the one responsible for robustness. This problem, unfortunately, is not very user-friendly, I would say. So it is a maximization problem of a cost function. Moreover, the function is nonlinear and the constraints are also nonlinear. So this type of programs in the literature are called concave programs. And unfortunately, there are no results really that allow to address this class of programs in the setting we are interested in. So nonlinear, cost, and constraints, plus infinite dimensional decision variables. So it seems to us that this problem is undocumented in the literature. Actually, if you have any pointer that could, where maybe you have seen something similar, that would be much appreciated. Of course, we did not give up here, and we built a number of methods that allow to actually compute the optimal value. It is actually a set of results that I'm going to close in a meta theorem, which is about the cost of ambiguity. So it is about the optimal cost of the maximization problem that you see there. Well, this meta theorem says that the optimal value is given by the summation of two functions. One is eta, and I recall you that eta is basically the ambiguity radius. So it is the function that defines how confident the agent is in its model, plus an additional term C tilde. C tilde comes as the optimal value of an optimization problem again. However, this optimization problem is a very user-friendly one because it is an optimization problem that involves a variable alpha, which is a standard scalar. So we switch from an infinite dimensional setting to a simple scalar optimization of this function v tilde, which I'm not going to give you the exact mathematical expression because it is a bit long, but the important takeaway is that this is a convex function. So in the end, we recast a very difficult infinite dimensional problem in green into a simple convex optimization, scalar optimization problem, which we can prove as a global minimum. And we can prove that the global minimum is always going to be positive. So going back to the architecture, the maximization free energy of the free energy can be tackled via a simple scalar convex optimization problem, and the cost is going to be non-negative. So the cost of ambiguity, we can give it a precise mathematical expression, this eta plus C tilde, which is non-negative. To me, the fact that the cost is non-negative is an interesting interpretation. So it means that if the agent is not confident in its own model, well, there is a price to pay. So ambiguity also implies a penalty, and there is no way that a rational optimal agent can exploit ambiguity to obtain better results. So we want to minimize now this cost function, but before getting there, let me just highlight the main functional steps up to now in the architecture. So we have a cost and a generative model. We can recast the maximization problem into a scalar optimization problem, and what we get is always going to be a cost of uncertainty that we found, at least empirically, it's going to have multiple minima, and it is going to be non-negative, of course. So we have a cost of ambiguity. How do we proceed? How do we go from here? Well, we have to solve this minimization problem in our architecture. This problem seems difficult, but it's actually a standard optimization problem, which has a very clean solution. So the optimal policy is a softmax distribution, and the optimal cost is the smallest possible free energy across all possible environments, which is a log moment generating function. Let's go back for a second to the policy. So this expression says that the softmax basically is a combination of QU, which is the policy from the generative model, and an exponential kernel. So the policy is basically a mixture between the baseline behavior that the agent would like to achieve and a behavior that is obtained by twisting the generative model with an exponential. Of course, if I have very high costs, the exponential will be very small. And this means that associated to a given action pair, there will be very low probability of selecting an action. So the optimal policy is a softmax, and we are going to sample from it to obtain our action. So continuing with information flow inside the architecture, well, we have our cost of ambiguity. We build from here the exponential kernel, the exponential in the formula. Then on the other side, we have the generative model QU. Let's say this was just a Gaussian in this very simple example, centered in 0, just like in the linear environment case. And in order to obtain the optimal policy, the model multiplies together and then normalizes these two shapes. What does this mean? This means that the model provides a compromise between the wishes of the generative model, who would like to keep it at 0, basically the position of the ball, for example, but with a compromise related to ambiguity, because you see here in the exponential kernel, there is a very low cost, there is a very high cost, and therefore the model is favoring, let's say, these actions in the middle. Now, let me go back to the example. Let me consider again the regulation problem. We can say that the previous algorithm was a free energy minimization policy without ambiguity. And we saw already that the problem would not be solved with this approach. Instead, if we apply our model, which we called distributionally robust free energy decision making, Dr. Freedom is an acronym that is totally work in progress here, we see that the ball is able to stay around 0. Of course, we are not able to stabilize perfectly the ball because there is ambiguity, there is noise, etc., etc. But definitely the model is not letting the ball escape out of the beam here. And let me jump to the second environment. So the second environment, as I mentioned before, is a robot that is moving in an environment with obstacles. And it has adverse conditions. Let's say it has adverse wind. In the setup I'm going to show, the model is just going to be the robot dynamics plus some Gaussian noise that emulates sensors, while the environment is going to be the same as the model dynamics, but in addition there is wind here. We decided for this application to have a non-informative generative model, which means that the probability densities of the generative model are both uniform distributions. So this means that the agent can just do anything according to the generative model, and the cost must emulate the presence of the obstacles. So as a matter of fact, the cost is non-convex. To be more specific, the cost we are using in the experiments is the one that you see below in the picture here. So here you see very high cost here and here in the white part, which means the presence of an obstacle. And the position, the destination that the agent would like to achieve is in the bottom left of the panel here. So we actually deployed this model into a real robot, so into a real test bed. So we went a little bit beyond simulations. And what you will see here is the behavior of our model when there is some wind that goes against the direction of motion. So for context, again, the robot would like to go here, avoiding the obstacles. So what you see now is our model deployed on the robot. You see that it is deployed in a way that real-time computations are possible. The robot avoids the obstacles. And now, as it approaches the destination, like here, something interesting to me happens. So the robot is kind of insecure about what to do. So it's trying to escape from a region, basically, of large ambiguity. And once it does this, it is able to find the path back to the final destination. So, of course, the robot achieves the final destination. And here you see other recordings, other simulations of our model deployed on the same robot, but starting from different initial conditions. So I presented our model, which is also suitable for real-time application and that enables this free energy minimization across ambiguity. Let me now briefly discuss in these last few minutes some of what we believe are cognitive implications of the model. The first one is that the model supports a theory of mind. In particular, the model allows us to estimate from the viewpoint of an external observer. So here you see the hat symbol means observations. So the model from observations allows us to estimate why a given action was taken by the agent. So now the agent has implemented our Dr. Freedom model. We know that the optimal policy is the softmax we already discussed. And the intuition is that lower probabilities are assigned to actions that have higher costs. So the idea is to exploit this clean structure for the policy. And in particular, the idea is to build an observer. So we have an external agent now that, given the observations, would like to reconstruct the best it can the cost that was driving the intentions of the agent. To do so, we use a feature selection. So we parameterize the cost linearly in a number of features. Features can be any nonlinear functions. By the way, these results here build directly on some of our published work. This is already in press. And we would like to see if, given a set of features, the external agent could reconstruct the cost. Now, without going too much into the details of the mathematics, the answer is that this is indeed possible, and it is actually possible to build an algorithm that allows for cost estimation. So in the figure here, the algorithm, given the features and the generative models, via maximum likelihood function, via maximum likelihood arguments, is allows to assign the optimal weights to each of the features, so that it can reconstruct the cost the best it can in the sense of likelihood or maximum likelihood. Of course, the likelihood function L is the likelihood for observed actions. Now, to see this in practice, let's go back to the robotic use case, so where this was the cost that the agent was using. Well, by running just 4 simulations of the robot, so using only 4 trajectories and using maximum likelihood arguments, we could basically reconstruct the cost that you see here. So you see that the cost basically is not the same, of course, as the original one, the one below, that is reconstructed with our algorithm, but it's kind of similar. It has the presence of the obstacles here in red and here in white. And in fact, when we use Dr. Freedom with this reconstructed cost, the agent is still able to go to the final destination, avoiding the obstacles. The other implication, very briefly, I would like to discuss is that the model allows to explain confident and insecure behaviors. In particular, as ambiguity shrinks, we can prove that our model returns the policy of an agent that knows everything about its own environment. So this agent, we call it an oracle in some sense, and nobody can outperform the policy. So this is a very rational agent that has done its research well on the environment, let's say, and knows what and can compute the optimal policy. This means that the policy of this optimal agent, which I would call a rational agent, can be understood by others. So others can infer what are the intentions of this oracle agent. And moreover, ambiguity cannot be exploited, as I was saying before, to obtain better performance. So there is always a price to pay if there are mismatches between our own beliefs in the model and the external world. The other situation I'd like to consider is when the agent is insecure about the model. So when ambiguity becomes large, our model shows that the optimal policy approaches the policy of the generative model. This means that the performance of the agent will only be as good as our prior allows. So imagine entering in a very dark room where we don't know anything basically now about the room. We would behave according to our beliefs. For example, for me would be to find and look the light switch. But this opens a number of questions. The fact that we approach a generative model as the ambiguity increases. First of all, this seems to say that if we are unsure about our models, we should ground actions in our prior beliefs. And then this opens the kind of philosophical question to me if we are as good as our priors allow. And if this is true, let's imagine we are now an agent that needs to survive within an environment. Is it better to obtain, to learn a specialized or a general purpose generative model? So that's a key question, I think, for evolution. And this also opens the way to a kind of learning process. So in machine learning, we can learn mathematical models of the environment. We can learn policies. That's the whole field of reinforcement learning. I argue here, what if there is another way, which is actually learning ambiguity? So it's a sort of epistemic search. And finally, it would be very interesting. The model also defining the performance limits enables some measure of for quantifying misinformation. So we can say what is the optimality gap as ambiguity increases or decreases. And I'd really like personally to use this quantity to study Dunning-Kruger effect, which is basically people with low skills that overestimate themselves. Now, I would like, in conclusion, to thank you all once again. So I presented our approach to minimize free energy across ambiguous environments. This gave us a model that consists of a formulation together with resolution methods. And for the model, we designed algorithms that are able to implement the policy. What I did not show is that another stream of work I'm doing with my group, which is actually understanding if there are implementations of these same policies that are not algorithmic and that can be implemented via biologically plausible neural networks. Again, I can give you the references if you're interested in this. And finally, I would like to thank Josefa, who is a PhD student, and Arash, who is a postdoc, who are the people working on this specific project that is funded by the European Community and the Italian Ministry for Research. I can leave you the presentation. I can send the presentation if you want. Here are just a few references for both the ambiguity and aware framework and the neural implementation. So with this, I would like to thank you all. And if you are interested in the preprint, please send me an email.
Well, thank you so much, Giovanni, for the presentation. It was super interesting. Surely someone will want the slides at some point.
Okay,
I will, so we can discuss later by email and we can circulate them. So now we can start the Q&A session. So let's see if there are any questions out there in the chat. So if anyone has any question, like feel free to raise your hand and you can ask anything. Maybe I just start with a very general. So how can you where's the exploration bit of reinforcement learning like explicitly in both, like just the first bit of the presentation, free energy minimization without the extra ambiguity constraint, and later on when you add that, where does that lie?
That's a very interesting question. Thank you, Miguel, because it's something we are working on actually. So at the moment, we don't know what is the optimal trade-off between learning ambiguity and exploiting it in the model. Our intuition suggests that this would give rise to behaviors like bacteria chemotaxis, where the agent basically stops for a little bit of time, explores what is nearby, and then moves to next step. So we observe in the robot, in fact, a sort of tumbling behavior for the agent at some point. What is open is that we don't have a mathematical answer on what is the optimal strategy to orchestrate exploration and exploitation.
Okay, cool. Thank you.
Yeah.
So let's see if there are any questions in the chat. I guess if there are no questions, maybe we can move to you, Carl. That's okay.
Well, I think you should questions.
What was it?
You should ask some questions.
Some more questions.
Yes. That's a glorious.
I mean, there's a lot to digest in this presentation.
Yeah, I know. Maybe it's a bit a lot. I tried to put a little bit of everything we are doing in this context.
Yeah, because I was so in the again to the exploration exploitation. So because if you just minimize variation, if you just minimize free energy, it seems that you're just fitting your model. But in order to have some exploration, you should have this minimizing complexity. So you cannot only minimize that complexity, right? Because you want to give some room to exploring some other state that might not minimize your complexity in the actual time step, but maybe in the future.
Yeah.
So I don't know if that ambiguity term is like sort of playing that role, kind of, when you try to minimize the worst scenario in which you can be in the ambiguity scenario, let's say.
Okay, so there are, I think, different things maybe that play a role in what you were saying. So first of all, the use of the generative model. Now, as I spoiled, I am an engineer, a control scientist in particular. So we tend to engineer the generative model, and we do that in a number of ways. So that we typically, for example, a generative model is extracted from examples. So we have people collecting data that they're doing a similar task, and that's going to be our generative model. Another way to do that is to embed a sort of passive dynamics. So this means that there is no control effort. So generative model will drive you towards a least energy state. And what is very important is the engineering the cost function. So in that case, it's really the cost function that plays an important role. Now, the thing is that the cost function is evaluated on average across the interactions between the agent and the environment. So if the ambiguity is there, you cannot perfectly evaluate what are these interactions. So and that's where you have that cost of ambiguity, which would become kind of large whenever the agent is not confident in the model and small otherwise. In fact, the function eta, that was that radius of ambiguity that let's say quantifies the discrepancies, we find it convenient to not have it constant, but having it, let's say, changing for every input state pairs. In particular, of course, it's kind of true from the intuitive viewpoint. The ambiguity should be small, close to the state that is your final goal. So it makes sense to invest time in learning much more closer to your final goal than at the beginning, maybe when you're far away from it.
Okay, so it's proportional then to the distance of your goal, let's say, so in some way.
Yeah.
Okay.
Yeah. And I did not talk about it, but what we can do is sort of quantify a regret of ambiguity in a sense. So we know what is the optimal cost of an ambiguity is 0. On the other hand, we know what is the optimal cost with ambiguity. So a good measure to maybe trigger some learning mechanism could be that of triggering it when the gap, the regret, is bigger than a given threshold.
Okay. Thanks.
Yeah.
Let's see, no questions from the discussion. Yeah, a lot to digest, I think.
Yeah. But again, I can give you the slides. Maybe I can send them to you by email.
Yeah, we can circulate them for anyone that's interested in that, sure. Okay, Carl, I see that you're showing yourself now.
Yeah, thank you for asking your question. Is it my turn now?
Yeah.
Thank you very much.
Absolutely. No worries.
So that was a really impressive presentation, and I think, Giovanni, as you noted, there's too much there really to even review, let alone admire. I think. Well, let me ask. So Miguel usually asks, what kind of feedback would you like? What kind of comment, or because we've already admired you, so you've done that bit. So what else would you like? What kind of
Well, my provocative question maybe is, I'm not a neuroscientist, so we have kind of the ambition of trying to put a control perspective into this decision-making free energy inspired. So would this view be compatible with the free energy principle, for example?
Right.
I'm very interested and keen in your feedback on that.
Okay. So the feedback you want then is the relationships of the approach that you've developed, developing and have established to the free energy principle, or applications of the free energy principle to decision making and action selection under uncertainty, with a special attention to its biomimetic aspects. Could it plausibly be implemented in a sort of neuromorphic or biomimetic fashion? Okay, right. Well, I think the answer to that the answer to that question is yes. I think there is a potentially intimate relationship between what you have presented and the free energy principle as applied to biomimetic decision making and movement. Having said that, I think you're going to it will be your responsibility to reveal that relationship and express it mathematically, because I think if you can, that will be really very useful. The way that these problems or issues are formalized in under the free energy principle has many common themes, but it also has some differences which I think, would usefully explain or possibly remove or dissolve by a suitable either transformation of variables or recasting your problem in terms of, to cut a long story short, converting an infinite dimensional function approximation problem into a finite dimensional functional approximation problem, which is the route that the free energy principle would take. So what I can do is just highlight some of the sort of key conceptual commonalities and then take you through how the standard literature in the free energy principle, and more specifically active inference, would deal with these issues and also reach the same conclusions that you have reached. The twist here, or the qualification, is that the maths in the active inference, which is the application of the free energy principle to decision-making under uncertainty and planning, that has this epistemic or curious aspect and is robust to uncertainty or random fluctuations or perturbations. Most, if not 99%, of that literature is in discrete state space models. Whereas I think what you're dealing with, in fact, explicitly, are continuous state space models. So what I can do is explain the equivalent formulation that you have brought to the table in the free energy principle, but I apologize, it will only be in discrete state spaces. Yeah. You will have to do all the heavy lifting to sort of reverse it.
Actually, it's interesting because we already did it. So the results also, we have versions for discrete spaces. In fact, when we deploy it on a robot, we need to discretize the models. Otherwise, they don't, it's just impossible. It is just impossible to estimate the integrals, to do the expectations, etc. So that bit has been done. And formally, it is very similar to what I showed you, except basically summations are replacing with integrals, but that's basically possible.
All right. Oh, good. So what I will go through then should be more familiar to you than it would be if you hadn't worked with discrete state space models. So I think the key points of contact are, first of all, realizing that to solve this kind of problem, you have to work with beliefs and probability distributions, as opposed to reinforcement, that you can actually do reinforcement learning without any explicit reference to optimizing not functions of the state, but functions of probability distributions or beliefs over states. And that's what I meant by the difference between optimizing a function as opposed to a functional, where the functional is a function of a function, and the function in question here is a probability distribution. So I think that's one, if you like, foundational commitment that is shared by your approach in the free energy principle. It works with functionals and probability distributions, nicely demonstrated by your definition of ambiguity as a radius in the space or probability distribution. So immediately that radius is a function of probability function. So it's a functional. And I think that's a big move, which you won't find, which is, if you like, I think takes you outside 20th century or standard approaches to optimal control. So, for example, in the setting of Markov decision processes with discrete state space models, the standard 20th century approach to this was to create a belief space MDP, which of course is a Hilbert space. It's infinite dimensional, impossible to solve. People sort of tried all sorts of function approximators and things to solve it. I haven't really seen any progress in that field for a decade or so. Whereas the active inference would say, no, would say exactly what you have said. No, that's not that's not the right space to work in. What you need to do is to convert your problem into an optimization problem where the objective function is now a functional of the belief spaces itself, and then you can actually solve the problem in real time in a mimetic way. So I think that's one key point of contact. The other point of contact is the importance of leveraging ambiguity in the sense that if you're acting optimally, then you will also have an aspect of information seeking and curiosity and novelty seeking that will allow you in the long term to resolve your uncertainty about the generative model so that you can pursue your preferred goals or your comply with the constraints that one has specified on optimal behavior from a control theoretic point of view. When phrased like that, there is a third, I think, intimate point of contact between active inference formulations and your formulation, which is a strange inversion, whereas in the if you're just trying to minimize free energy, you're trying to minimize the KL divergence, that is, say, the complexity term or the difference between your true, for example, true model or true posterior and your approximate posterior, or the difference between your P and your Q, for example. Whereas as soon as you move into the future, and as soon as you think about the consequences of action, then that flips, and you have this this reversal. So now you want to maximize the KL divergence, and that came across in your presentation in terms of having this sort of min-max or minimax, or sort of counterintuitive maximizing the free energy, but when and only when considering the consequences of the policy U. And that's really important, and that's exactly what emerges in discrete state-space treatments of active inference or the free energy principle. It manifests in the context of functionals in terms of something called expected free energy in active inference. But I'll show you what I mean by that in a moment. I'll share my screen and just take you through some references that you can just look at the functional form of the objective functions. And I'm hoping you'll be able to identify ways of by making certain assumptions about your radius or about the way that ambiguity is manifest, you can actually show that the expected free energy plays the same role as your approximate cost based upon or the approximate cost of ambiguity, as it were. However, because you presented so much, and you presented it as an engineer as opposed to the kind of ways that I would understand things, I don't know. So I'm just hoping you will be able to see how to join the dots. I can't do that for you, but if I tell you if I tell you how we would express this mathematically, my hope is that you will be able to say, well, look, these are just two ways of looking at the same problem, and thereby, I think, importantly, lend both approaches a construct validity. They're reaching the same conclusion. Simple things like, yes, the limiting cases under linear models, they reduce to KL control under a KL control under a linear state space model becomes linear quadratic control. These things are also true of the expected free energy. So if they have the same, if you like, limit cases, and they have the same conceptual fundaments, my hope is that they both actually share the same mathematical formulation, but just expressed in a slightly different way, or not slightly, in a very different way. If it was slightly, I'd be able to tell you what the relationship was, but I can't, so they are very different. Before I do that, though, there is an interesting, just speaking to the second part of the feedback in terms of this biomimetic aspect. Before we start talking about expected free energy. I just wanted to address, is this biologically plausible? In one sense, there is a literature on motor control and optimal control in a neurobiological setting that I think can be answered without worrying about ambiguity and the future and searching over the space of generative models, or certainly identifying the uncertainty about generative models and then acting in a way to resolve that uncertainty or that ambiguity. And that's simply understanding reflexive action in continuous state space models without having this epistemic aspect to it. That there are lots of very simple ways of implementing biologically realistic reflex actions that are much closer to state action policies. So although in your presentation you were careful to say that when you have the K subscript on the P, that allows for different control dependencies on the states to vary over time into the future. So in my world, that would basically be beyond state action policy optimization into sequential policy optimization. Given that distinction, given that I am just now interested in determining what the next move, the next control value is given my current state and uncertainty about that state, I would look at that as optimizing a state action policy, because it's not an optimization of a sequence of different moves that might actually have consequences, not just about the state I end in, but what I know about, or what my uncertainty is about latent states or latent parameters in the generative model. So in the very simple setting of state action policies that can be cast in terms of free energy minimizing processes, that literature is in continuous state spaces, and it just uses generative models, usually with autonomous dynamics, to generate biological motion, like sort of walking or handwriting and the like. And the idea here, the big idea here, is to dispense with the sort of forward inverse modeling you'll find in the motor control literature in neurobiology, and note that if you've got a generative model that can produce the right predictions of all the consequences of action, then it is sufficient just to engage reflexes that bring about the predicted observations. And these observations can be in a visual modality, or more importantly, they can be in a proprioceptive modality, say a telemetry or some feedback from the actuators, say in a robot. So in neurobiology, these would be proprioceptive inputs, which means that the finding the control that brings about the predicted proprioceptive consequences of an action is a very, very simple problem. So, for example, if part of your sensory input or your sensors, imagine you've got sort of LiDAR or RGB or some sort of way of assessing visual input or the positions of the objects in the environment. But now, in addition, you simply had input that told you about the torque on various actuators in your robot, or the velocity of some motor driving it in one direction or another direction. This would be the proprioceptive input. And if you've got a good generative model that can generate not just the sensors such as, say, LiDAR, but also predict the proprioceptive input, then you can use reflexes outside the generative model to make those predictions come true. So if you've got a good generative model, you can always make it come true by now acting in a way to minimize a cost function in observation space or sensor space. And this was a sort of key move at the introduction of active inference, nearly a decade or so ago. as a way that the biological organisms actually act. They don't have any notion of movement. They're not doing any planning. Certainly a thermostat or a virus wouldn't have a notion of planning or sequential optimization. All they know is that their proprioceptive input seems to change in this way when their thermoregulatory or thermal input or the visual input changes in that kind of way, and they can predict that. And if they can predict the proprioceptive as correlates of some sensory, other kind of exteroceptive sensory information, and then they're equipped with a reflex that makes that prediction come true, they can respond very adaptively, very, very quickly and very efficiently to anything with a state action policy. And furthermore, that particular construct, which is the biomimetic, if you like, implementation of motor control, is robust to the perturbations you talked about, because the perturbation is only registered in, the perturbation can be registered by sensing it. And of course, that means that you're now re-engaging the same reflexes to undo the effect of the perturbation, to make sure that your predictions now align, your observations now align with your predictions. So there's quite a lot of work implementing this very simple, effectively a Bayesian filtering scheme or predictive coding that was equipped with reflexes as a metaphor for biomimetic state action policy optimization, which is not what we're interested in here. I'm just qualifying this and showing that it was much more robust than any sort of open loop control that people were conventionally using in motor control theory in neurobiology, and generalizing the notion of linear quadratic control and you're having a Kalman filter to an extended Kalman-Bucy filter with lots of nonlinearities in, and putting autonomous dynamics into the generative model of a Kalman-Bucy filter, so that you could actually you could generate very realistic biological movement simply by realizing predictions on the basis of this sort of reflex arcs, minimizing the discrepancy between what you predict to sense and what you're actually sensing. So I thought that was an interesting that would be one answer to the is this biomimetic? Well, if you are devising a biomimetic scheme, then the first thing I would be looking for is whether the motors are being driven simply by the imperative to minimize the prediction errors that it can minimize, and basically changing the data. And the way that one expresses that in terms of the free energy is that you've got, if you think about the free energy functional, you've got, for example, one way of writing that would be the log probability of the data minus the KL divergence between the approximate and true posterior. Is that right? Yes, it is. Yeah. So how can I now use that? How can I now distinguish between perception and action, where perception is in the brain and action is in my muscles? Well, first of all, note that perception is about optimizing Q, and the only part of the free energy functional that depends upon Q is the KL divergence between your approximate and true posterior. So that doesn't have any effect on the log probability of the data, which you could actually interpret in terms of your cost constraints, your small c's, for example. So you basically do your perception by changing Q, or the sufficient statistics of Q, or the parameterization of Q, to make it a better belief structure that can, in predictive coding, generate predictions. But what about action? Well, action can't change Q, but it can change Y. So if you're minimizing action with respect to the free energy, what would that look like? Well, now you can rearrange the free energy to express it as an accuracy minus a complexity. So now what you've got is an accuracy term, which is the expectation of the log probability of your sensory input under your approximate posterior, minus a complexity term, which is the KL between the posterior and the prior. Again, from the point of view of perception, you want to minimize the complexity whilst maximizing the accuracy, but we've already done complexity. We've already done perception and optimizing Q. Now we want to optimize U, and U is simply going to change the data. So now I've got the accuracy term, which is the expected log probability of the data, which of course depends upon the way that it's sampled. And certainly if it's proprioceptive, it depends very directly and explicitly on my action. So I now optimize the accuracy with respect to the control variable. So now I've got a setup in which I can describe biomimetic action as simply a gradient descent on free energy, which just transpires to be a minimization of the proprioceptive prediction error for action, and the minimization of prediction error with respect to the generative model, which is the predictions. So I'll show you my favorite example of that, which is a very early one, in a second, just so you can get one of your students to go and read about it and do a 100-word executive summary. But I want to make a key point here. I keep saying this is a very simple kind of control, because notice there's no belief about you. There's no planning. There's no beliefs about you in the future. So you in the future doesn't exist yet. So it becomes a random variable. So now you have to infer it, and you get into planning as inference. So I think that's where your story is. It's much more planning as inference, sequential policy optimization. You is a random variable. However, having said that, it may still be the case biomimetically that the predictions of your generative model, even accounting for beliefs about you and the ambiguity about those beliefs, or the generative model under which those beliefs are optimized, the actual realization of the predictions may still be biomimetically in terms of a U, which is a real variable. And in fact, we call it A to make sure that people don't get confused. It's not the random variable U in the generative model. It's just action. It's got nothing to do with the generative model. It just sits on the robot and it just reflexively controls things, just like a servo or feedback control. So that sets me up to now tackle the thing that you're going to be much more interested in, which is the way the emergence of these themes in terms of answering the question exactly as you posed it in your introduction. Normally, generative modeling is all about optimizing a posterior over latent states of the world that best explains some input. However, this does not account for action if now I am thinking about acting in the future, because action, U now becomes a random variable. So now I need a distribution over both the latent states and U, which means I can now factorize it exactly in the way you did. I can now build a probability distribution, technically a posterior predictive distribution over states of the world conditioned upon U. And now I am obliged now, in fact, there's no other way that you can sort of express this mathematically. I now induce a prior over U. Now, what sort of prior am I going to choose? Well, I'm going to choose that which minimizes the expected free energy under all the observations that I would get if I acted like that. So, but now the observations become a random variable. So now you've got a much more encompassing inference problem, where now you want to evaluate the joint distribution over outcomes, the observations, and the latent states causing those observations, or one of the two, depending if you know the likelihood mapping, conditioned upon you. So now your functional becomes a functional of a belief distribution conditioned upon you, in a very similar way to the way that you were articulating, sort of, and in fact you actually conditioned you on the previous state. I'm doing that implicitly in the sense that I'm talking about a posterior predictive density. So, given what I've seen so far, what are my beliefs about the state of the world in the future, and how does that depend upon the sequence of actions that I prosecuted? What happens from the point of view of the physics, and perhaps I should again, this is going to be in the same way you gave us too much, I'm giving you too much, but there is actually a physics backstory to this. If you just work from self-organizing random dynamical systems and work out what the flow of their control variables must be if there is some attracting set, you can actually derive the probability distribution as a function of, or conditioned upon, current states over over U, and then you can sort of lift that functional form and put it into a sort of partially observed Markov decision process. In so doing, you create something called an expected free energy. So this is a functional that I think plays exactly the same role as your implicit functionals when you'd actually re-articulated the infinite dimensional optimization problem into a finite dimensional one towards the end of your presentation. So we would call that the expected free energy. And it has a very similar functional form to the variational free energy, but it has this interesting twist that you were talking about, which is basically, instead of trying to minimize the KL divergence, a rearrangement means you're trying to maximize it, and that maximization underwrites the curiosity you were talking about, because you can read that KL divergence as a mutual information or an information gain, and suddenly, simply because observations in the future are now random variables, you're now interpreting basically the KL divergence as the reverse KL divergence, now that you want to actually maximize and get the most information you can. So that's the basic story. If you'll indulge, I appreciate I'm talking a lot, but I also know this has been recorded, so that you can
I can go back in case.
You can go back, or you can get your one of your students to go back and summarize things. But if I just try to how do you do this? Oh, I am possibly now sharing, am I?
Yeah, but I see black screen.
Yeah, we usually have to wait a little bit until it catches up.
Okay.
So it certainly thinks it's doing that, and if it doesn't, I'll try again.
Okay.
Are you there? Yeah.
Yep.
That's very good. Where are we? That's you, TMB beating that. This is my simulation of continuous behavior, interestingly, but that's not what I'm after here. Let's try and get rid of all this. What's that? Go away. And we want this thing here. Yeah. So this is a figure from my favorite paper about this sort of biomimetic formulation of motor behavior, without trying to address the deep problem of planning and representing action as part of the generative model, which is what you're trying to do. So this is really simple. Some people call it merely reflexive active inference, just to emphasize it's the kind of behavior you could elicit or model in a thermostat, in a virus, or a very simple walking machine, for example, because there's no inference about the control. It's just, I've got predictions about this nice world that has this right kind of rhythmicity, and all I need to do is to make those predictions come true by maximizing the accuracy of my predictions by changing the data reflexively. And the reason I'm showing this figure, which was actually a simulation of handwriting, so this little agent just was able to sort of write out JA, JA, JA ad infinitum, but as with earlier versions of this, it was interesting to see what would happen if a wind pushed the hand in one direction or another, if there's a perturbation that was not part of the generative model. And because this is all written down or expressed in terms of stochastic state space models with state noise and observation noise that are themselves inferred. Well, no, because the actual behavior depends upon minimizing prediction error, the exogenous perturbations or fluctuations are relatively easily cancelled, because that's where they are expressed irrespective of the generative model. The generative model just provides a set point or a trajectory or a path that is very robust to perturbations. So you can look at this at your leisure if you wanted to, but just to highlight the fact that this was there. But more interesting from your point of view is the biometric run through under continuous state space models. And interestingly, pursuing the biometric theme, just saying that if we had these kinds of very simple models of our own created sensorium, our self-generated patterns of sensations, we could use the same generative model to explain not only the consequences of me acting, but you generating the same consequences if you acted. So part of the biomimetic focus here was trying to make the point that if you could get the right kind of generative models for active inference, then you could use them to explain things like mirror neurons. So that was another sort of biological. It was another biomimetic aspect of this paper. So this was an early paper in biological cybernetics. Yes, biological cybernetics by Tristan Charamatou and James Kilmer. You're over 10 years ago now.
Thank you.
So that's really for your entertainment and interest. But I do repeat, even if you're using very sophisticated planning as inference, the actual implementation may actually, if it was biomimetic, acquire a degree of robustness to fluctuations or perturbations of a certain kind, not due to uncertainty, somebody's closed this road or put an obstacle in my way, but things like wind and waves, for example. You may find robustness for free with this more biomimetic approach. But the real treatment I wanted to there's only two more papers here. The real treatment I wanted just to sort of briefly, there are lots of papers on this. I've just chosen this one because it was written by a mathematician, Lance da Costa, and I got the impression that you like maths and being very crisp and formal. So I'm suggesting this one. But I do repeat, it's in discrete state spaces. And probably the most interesting one for you is summarized in this figure here. So what this figure is trying to do is just trying to summarize the functional forms very, very much as you were.
Exactly.
So the idea here is that we're splitting the optimization problem that is now being cast purely as in terms of inference and variational inference into two parts, exactly like you were. The first of all is, what are the latent states of the plant and the world given a particular policy, which is going to be a sequence of control variables u in the future at time t. And we're going to sort of say, we're going to minimize my beliefs about states of the world at the moment by minimizing variation-free energy in the usual way, by finding the least complex but accurate explanation, which can now be gracefully connected to machine learning in terms of maximizing the elbow or evidence lower bound in the usual way. So just to highlight the alternative ways of doing that. So here complexity is just the KL between the posterior and your prior, and the accuracy is in the usual way the expected log probability of the outcomes given your beliefs about the causes of those outcomes. And then you move to your, if you like, your empirical prior over the policy. noting that it does depend upon the inferred states, because you now use your posterior predictive density over the states of the world conditioned upon your policy to form an expected free energy. It is this thing, I think, that is where you move to your maximization, or the thing you want to minimize. And interestingly, it does use the same kind of words, but in a slightly different context. So this is not a variational bound. It is simply the kind of prior over policies or sequential actions or control variables that are random variables in the future that will lead to the preferred states, where the preferred states are those that minimize the free energy. However, having said that, it has a very, very similar functional form to the free energy. And I noticed that you were sort of referring to your objective function for planning or sequential policy optimization as a free energy. I think you're perfectly entitled to do that, because a free energy, what is it? It's just a relative entropy plus a potential or expectation of some low probability. But I think you should make it clear it's not the variational free energy used for inference or perception. It's a new kind of free energy. And hopefully you'll be able to say very much like expected free energy in active inference formulations. Having said that, I repeat though that I think the parallel in the functional forms is actually very telling. So this expected free energy is just a functional, and it can be rearranged in exactly the same way that we rearrange the complexity and accuracy into an evidence bound and log evidence, in terms of risk and ambiguity, and by just switching a few terms around the intrinsic value and the extrinsic value, where this corresponds to your constraints or your costs. So you just replace this log P of outcomes in the future with the C's that have these very simple constraints, that such that certain outcomes are going to be highly unlikely, like touching contact points or falling off the edge of the table and the like, or sensing yourself falling off the edge of the table and the like. The interesting thing here is that when one looks at the evidence bound as a KR divergence, we're trying to minimize it. But when we take its expectation effectively under outcomes that have yet to be observed, conditioned upon the policy, we now want to maximize effectively the KR divergence, because now the O is a random variable, so it goes to the other side of the KR divergence. So it now becomes a reverse KR divergence, which now you want to maximize. And this KR divergence has exactly the same functional form as Bayesian surprise in the visual search literature. And it is just the mutual information between the outcomes or the consequences and the latent states that are causing them, as revealed under this policy. So I've loosely, Lance in this paper, loosely associated this with not just the Infomax principle, but also the notion of intrinsic motivation you get from the Parisian neuroroboticists, because it's this information-seeking, uncertainty-resolving kind of KL, reflecting the KL as an information gain. So you've got, exactly like you had, you've got this sort of constraints, these pragmatic constraints articulated by C, plus this expected information gain or intrinsic value or epistemic value. You use the word epistemic. I like using that word a lot. And notice that what this does is that it dissolves the thing that you brought up with Miguel, which was this: it dissolves the exploration dilemma, simply because your constraints are now have the same currency as your expected information gain because you've written down your constraints as a negative log probability, so they now have natural units in the usual way, which means that depending upon what you don't know about your environment, the intrinsic value or the epistemic value may dominate over the constraints, so that you will explore up until a point that the intrinsic value falls below the pragmatic value or the extrinsic value, and the constraints kick in. And what tends to happen when you simulate this kind of planning is that the agent will explore its environment under the constraints until it gets bored. And when it gets bored, when it thinks it knows everything, there's no more information gain. And then it becomes confident in exactly the way you were describing. And then it becomes exploitative. It just conforms to its constraints and goes for its preferred position, or seeks out food, depending upon the precision of these constraints. Sometimes in our literature, referred to as prior preferences. So, but I actually prefer the notion of constraints to that. I think it's a more useful one. And then, so you may be asking, well, where's the ambiguity then? Well, ambiguity in this form of functional form has a much simpler meaning. I'm trying, I'm just trying to think whether one can bring, because your ambiguity is in the space of models.
In fact, I was wondering if ambiguity was the right term for us now, looking at this figure here. So or should that be confidence in the model? I was just wondering about that.
It's certainly, yeah. No, I think you're free to choose the term. The reason, yeah, I think it is confidence in the model, in the structure of the model, the form of the model, and you could just talk about it being a precision or an imprecision or ambiguity. I think you're perfectly entitled to call it ambiguity. It's this ambiguity pertain to uncertainty over the space of models. I think that's the key thing. Whereas in this instance, it's ambiguity over the space of hidden states. Now, of course, you could say that certain hidden states, like the parameters of a generative model, parameterize the model, and that you could say, well, a model really is defined by its parameters or certain sort of areas of parameters, say within your radius, and that you could now rewrite the uncertainty over models, where the model is the joint distribution over the system's S's and O's. Or you could think about that as each different model, basically in the same structure of the model, but under different parameters. And you could also now think of the different latents here as being parameters. So I think you probably should use the word ambiguity, but just make it clear that it's over what space, what event space is the ambiguity. And for you, it's very explicitly the functional form of the generative model itself. But no, you could express differences in the functional form in terms of limiting cases of different parameters, and then therefore it's ambiguous about parameters. And you could actually treat parameters as very slowly moving latent states. So you could also think of this, at least conceptually, as ambiguity over uncertainty about states, and in which case they would be the same thing, I think. Yeah. But this is exactly the kind of joining the dots that I was saying you would have to do, given your understanding of the implementation that you presented.
And the other connection is about the reflexive control. So that's actually what we do now. That's something that sparked in my mind. That's something that we do when we actually engineer this stuff. Because there are situations where we cannot afford to compute the cost to go, basically. So there is no planning, there is no time for planning. And in that case, basically there is no cost to go. So the model becomes very fast, and the generative model plays a key role. So it is typically the generative model that drives the intentions of the actions of the agent in that setting. So that's something that from the engineering viewpoint, we are finding as well.
Oh, right. Yes. Well, that is very reassuring because I mean, if you work in robotics, then what you do has to work, and therefore it has to be biomimetic. So I'm not surprised that ultimately you leverage that sort of biomimetic aspect. Yeah. I'll certainly give you a certain kind of robustness beyond being robust to people changing the environment, or this the kind that you would need to resolve by exploratory behavior. Yeah, absolutely. I was just trying to justify why we use the word ambiguity. It really inherits from economics, in the sense that you in economics, well, first of all, just looking at each of these terms, this risk term here is exactly the term you mentioned in terms of KL control. It's just basically picking that policy that brings my posterior predictive beliefs about the states close to some prior or preferred or constrained states. And that is KL control. But in economics, that's also usually read as risk-sensitive policies. Which means that the other kind is the ambiguity. If you remove the ambiguity as well, then you can get back to expected utility theory, or indeed right back to James's maximum entropy principle, which is, I think, another way of expressing this sort of slightly paradoxical maximizing free energy that you talked about. I think what you were talking about is, not unrelated to the maximization of entropy just during keeping your options open during inference itself, where it becomes very precise in terms of a relative entropy of information gain when you move to planning, which James did not do, but you can if you wanted to sort of make that conceptual link. So the ambiguity, the word ambiguity here is largely to speak to economists, simply because you can divide different kinds of uncertainty into risk and ambiguity, where the risk is, if you like, uncertainty about the consequences of my action, whereas ambiguity is just not knowing the game that I'm playing. For you, it's the model I'm using, but as articulated here, it's just not knowing. Well, you actually use the example that I use as well, which is being in a dark room. So being in a dark room means that the likelihood mapping between the state of affairs, the latent states in the room, and the outcomes has maximum ambiguity or zero precision. So that there is any change in the state of the room produces no change or maximum entropy distribution over outcomes. So the first thing that would happen in terms of minimizing expected free energy is to switch the lights on. So I like that because that's exactly the example we use. So the ambiguity there is the darkness. You don't put yourself in a situation where you can't move or you can't see anything, where there's no there is no precise likelihood mapping between the causes of your observations. That now becomes an important part of the information gain when it sort of moves over, and you rearrange it. You can express the risk in terms of outcomes or states, should you want to. That's to get from this kind of well, you can see how we've just swapped these two things around. In order to show the ambiguity is an important part of the curiosity. The last point I wanted to make was just talking about this link between what's the real difference between a structure, this functional form for a model or a generative model, the space of P's, and the different parameters that could parameterize each of these different models, or indeed the different states that could be regarded as very slowly changing parameters. I don't think there's a massive difference, but it's important to acknowledge that there are different kinds of unknowns in this game. Exactly the same difference pertains to that information gain, or that expected information gain, or that epistemic or intrinsic motivation term. You can apply either to states or to parameters. And when it's applied to parameters, you hit in this example, which comes from the same paper that I was talking about earlier, which is the oh no, it's not. My apologies. This is a different paper. Okay, so sorry. Yeah, this is active inference, curiosity, and insight. But the reason I put this there was just to make the important conceptual point, which I think it maybe you would want to make as well, that you can apply the expected information gain to states of the world. So if I look behind this door, what's hiding behind this door? Or to the parameters of the generative model. So can I open this door? So a good epistemic action is basically trying to open the door, and then I know whether this door is locked or not locked. Basically, that's a parameter of my world. I'm just wondering whether you can take exactly the same notion and apply this to the model itself. I'm just wondering if what you have done is basically taken the expected information gain, not to the parameters of a model or the states of a model, but to the functional form of the model itself, and therefore implicitly introduced a curiosity about the model structure, about
if I get it right, what we did was not to impose any policy structure a priori. So there are no policy parameters here. Although parameters, if we would consider them as random variables in Bayesian terms, we could extend the framework to also include parameters. That would be just like, formally, I would imagine it would be an additional state variable for us.
Yes, yeah, and indeed, in the filtering literature, that's what people do, isn't it? They just augment the state space with some slowly fluctuating states, and then call them parameters. And I think that's again a very biomimetic, way of dealing with that. Yeah. In my world, we're sort of say the inversion of a generative model to infer the latent states is distinct from learning the parameters, but again, it's a slightly blurred line if you treat the parameters as slowly varying, states.
Yeah.
Well, that is my feedback. I hope
that was a lot as well. So you paid back on the amount of information, and that is very interesting, and we'll take a look at all the points here. That's I didn't know about the reflexive literature, so that's definitely we will look into that, because I think we do some of that because it's the most natural choice for many applications that we have. And about the robustness, another finding that I did not really discuss was that sometimes if you forget about the ambiguity constraint, it's like these free energy functionals are by themselves robust. Now, what you said, I might interpret that this robustness might very much be due to the generative model. So maybe it is a matter of changing the model, and we would also observe also in other applications, let's say, a lack of robustness as there are mismatches. So that's what maybe one thing definitely we need to look at.
Well, that's interesting. You might then I can guess what might be happening there is that if you're optimizing the model itself, you've been optimizing it implicitly with respect to the marginal likelihood or the negative variation free energy, and that means you'll be minimizing the complexity. And if you have a minimally complex model, that's going to be more robust to slight variations. If that's true, there is a small literature showing that minimizing variational free energy is dual to the James's maximum entropy principle.
Yeah.
So mathematically, they're the same thing. So that'd be a nice point of contact to be able to say that baked into these variational approaches is a certain kind of optimal robustness that maximizes the uncertainty pertaining to learned or inferred parameters. That is at the heart of measurement physics.
Okay.
Because that that is dual to James's maximum entry principle.
Mm.
And when the uncertainties are over trajectories as opposed to pointwise current states or parameters, that's called the maximum caliber principle. So it may not mean a lot to everybody, but I think that's a really, because it just validates the whole approach. If you can say, well, this shares the same foundations as physics, the most generic formulation of physics, I think you know you're on the right. You know you're on the right.
I think your intuition is right, because I think, I mean, what we empirically found is that the generative models that are more robust are basically the uniform distributions, which are the least informative. So it's
yes.
And in this case, the pullback library becomes the entropy minus the entropy. So yeah, that's something definitely that we should look into and expand upon.
Yeah, well, in a sense, you don't need to, because you're already using it. I was suggesting you just tell the reader that this is another way of looking at this. Just for your interest, exactly the same thing happens in statistics as well. That to make your statistical inference robust to random effects, you have to explicitly minimize the complexity. And if you're using priors, you also have to use the least informative priors. And sometimes I call Jeffrey's priors a good, nice example of that in the statistics literature. If it's over a bounded state space, then absolutely uniform priors. And James actually, I think, spent a lot of his time working out the sort of the nature of these maximally uninformed priors in unbounded state spaces, and actually derived the difference between continuous and differential entropy for continuous variables. So they're very important, these maximum entropy priors, just to give you that space and that simplicity in terms of your predictions or your accuracy. Again, I don't think that practically you've already solved the problem, but I think these are really interesting mathematical and conceptual points that you can make just to just join the dots.
That's great. That's thank you very much for all the feedback. That's been really valuable.
My pleasure. So if Miguel is now usually stops us talking and makes us clap, that's what normally happens.
Cool. Thank you so much, everyone. Thank you, Giovanni, and thanks, Carl, for your feedback as well, as always. Let's give final round of applause to Giovanni for the presentation. Thank you so much for that. Very interesting. If you want to share them by email, like the slides, and maybe if anyone contacts us and with your permission, we can circulate them if you want.
Absolutely. No problem. I'll send you the slides. Okay.
Perfect. Thank you so much.
Thank you. Nice to meet you.
See you next time.
Bye.